Hello everybody. Today we're going to answer the question, how can we get fair results from a biased coin? This is a typical probability quiz often asked in analytics interviews. For instance, if you're applying for a data scientist or statistician position, it's quite likely that this question may come up during your interview. The interviewer might ask, how would you obtain a fair outcome from a coin without knowing the probability of heads? Or simply, how would you get a fair result from a coin without knowing whether it's fair or not? Today, we're going to explore how to tackle this question using the von Neumann method. We'll begin by setting up the classical coin flipping scenario. We have a coin with two possible outcomes, head or tail. Each flip is independent, and the probability of obtaining a head is defined as p, a number between 0 and 1. Consequently, the probability of obtaining a tail is 1 minus p, which we call q. The von Neumann method suggests that when we are unsure whether the coin is fair, we should flip the coin twice. Let's look at the possible outcomes. If we get head on the first flip and tail on the second flip, we consider that a valid outcome and we retain the first result, head. If we get tail on the first flip and head on the second flip, we also retain the first result, tail. But if we get the same outcome twice, head, head, tail, tail, we discard and flip again. That being said, we see that we have four possible combinations. We can define the probability of the event valid as the probability of the event head times the probability of the event tail plus the probability of the event tail times the probability of the event head. Similarly, we can define the probability of the event discard as the sum of 2 times the probability of the event head and 2 times the probability of the event tail. Now let's define the probability of eventually getting a valid outcome. This means, after possibly repeating the process multiple times, we finally obtain the combination head-tail or tail-head. If we are lucky, we might get a valid outcome right away. If not, we may need to discard once or even twice before getting a valid outcome. Now, we see that if we factor out this element, it's clear that we are dealing with a geometric series. So, we apply the geometric sum formula to express this in a clearer way. By organizing the denominator and rewriting q as 1 minus p, we can expand the square and simplify some algebra steps and get to the point where we see that such probability is equal to 1 over 2. This tells us that despite the bias, the probability of finally returning a valid outcome is always 1 over 2. Fairness is preserved. Now let's explore the probability of discard again. As we said before, this probability is equal to 2 times the probability of the event head plus 2 times the probability of the event tail. We can rewrite this q as 1 minus p, and rearranging the term, we get to the expression of a parabola. We calculate now the first derivative, and we want to find the stationary point So we equal the first derivative to 0, and we discover that p equal to 1 over 2 is a stationary point. Given that the second derivative is greater than 0, we also discover that such a stationary point is a minimum. Let's evaluate the value of the discard probability at the minimum and at the extremes of p. Here, we evaluate the probability of discard at point p equal 1 over 2. The value of such probability is 1 over 2. Point 2 and point 3 evaluate the probability of discard at point p equal to 0 and p equal to 1, and they both give value 1. Now, we can briefly sketch the probability of discard against the value of p. And we can see that the minimum of the parabola is achieved when p is equal to 1 over 2, which gives back a probability of discard of 1 over 2, which means essentially that when our coin is fair, also the probability of discard is fair in a sense. Whenever we are dealing with an unfair coin, so we deviate from 1 over 2, either to the right or to the left, we can see that the probability of discard increases. In other words, this means that the more unfair the coin is, the further we move from 1 over 2, the higher the probability of discard, and the longer it takes to get a valid result. Let's now simulate a real case where we suppose that the probability of head is 0.8. As this is a highly unbalanced coin, we employ the von Neumann method. We see that on the first try, we get tail on both flips, therefore we reject this result. The same occurs on the second try, where we get head on both flips. On the third try, we get head and tail, therefore we retain head as final outcome. So this is a valid result. We could stop here. If we assume to have a fourth try that returns tail on the first flip and head on the second flip, this would also be a valid outcome, and we would retain as a final result tail. As we can see, both valid outcomes, head and tail and head, occur with the same probability, 0.8 times 0.2, which returns 0.16. So the method is fair. To conclude this video, we have shown how it's possible to generate a fair result from a biased coin using the von Neumann's method. It guarantees fairness regardless of the underlying bias of the coin, even though we've seen that a more biased coin means that we may need to wait longer for a usable outcome.